Hello, everyone. Welcome back. Today, we're learning about maxima and minima, or maximums, and we call maximums and minimums. These are, as we'll see, kind of like the high points or low points of functions. So our goals, we find two types, basically. What if I'm called the absolute maximum minimum values? Then we find what are called local maximum minimum values, and also be able to find the critical points of a function which are related. So first, let's kind of talk about the definition, the mathematical definition, then we'll explain what it means. So it says you have some function f, it's like a regular function we think about, on some set D, think of D like the domain, containing a number C. Okay, that's our x value, it's some x value. Then if you plug that x value into f, or essentially if the y value for that C is bigger than the y value for every other x in that domain, in that group, that set of numbers, that's called the absolute maximum. Okay, that y value is called the absolute maximum. That's the highest point of the graph anywhere, the highest point of the function. And then similarly, if it's less, that y value that goes with C is less than every other y value, that's the absolute minimum. So that was kind of mathematical. Let's come over and explain this. So let's take a look. So let's look at a few graphs to kind of make sense of this. All right. So, well, in many ways this can happen is, let's say this is our function. Oh, actually, let's not put arrows. Let's say it stops. Well, let's do that again. Okay, so let's say I have a function that looks like this. Okay. Now, let's label a couple points. Let's say this x value right here is C, and let's say this one is actually D. Okay. So what this says right here, this y value, see, obviously this is the highest point on this graph. Okay, the y value is. So if I plug in f of C, that y value is what's called the absolute maximum. That's the highest point on the entire graph. And here we have it defined between these 2 points here and here. Okay. Now, this point like this can be the top of the hill, but doesn't have to be. Okay. Now look at our lowest point on the graph. That's obviously right here. So f of D is what's called the absolute minimum value. That's the lowest point in the graph. That can occur at an endpoint like this or somewhere in between. Okay, either one can. Okay, so that's the basic idea. Look at the highest point of the graph or the lowest point of the graph. Once again, that can occur at the end point, or anywhere in between. Now, a couple of things. It doesn't have to be a nice, really nice graph like this. Some kind of unusual things can happen. Okay, so let's draw another one. So a function looks like this. So it starts here, maybe kind of like this one. But let's say it looks like this. It looks like this. Okay. So here I'm just showing some examples of different things that can happen. Okay. Now in this case, this y value is your absolute maximum. Although the graph isn't continuous, it doesn't say anything about that, because basically this y value is higher than all the other y values there. That makes it the absolute maximum value. That's the highest possible value. Now this one, okay, this function actually has two values that are actually top of the lowest point on the graph. These two are actually absolute minimum values. Both of them are, because they're both the same y value. And they're at the lowest points on the graph. And once again, it doesn't have to be continuous. Okay. So both those are absolute minimums. So those are kind of some of the kind of things that can happen. So the graph doesn't have to be continuous, or doesn't have to be a nice function. You have holes and gaps and all that. Basically, looking for the highest point and the lowest point. Okay. Now, there are a couple ways you can also have something where it has no absolute maximum or minimum. So let's talk about that. In fact, a good example of that is the graph. If you have f of x equals 1 over x, that's a good example of this. You've seen this before. It looks like this. Okay, so on this side of the y-axis and on this side of the y-axis. Okay, notice the arrows means it keeps going forever in every direction. Okay. Remember, it has a vertical asymptote here at 0 because y can't be 0. So if you notice, this graph keeps going up forever. Okay. It never stops decreasing. So as you can imagine, there is no absolute maximum. This is always going to increase. Okay. The closer we get, the closer x gets to 0, the more y goes toward infinity. So there is no absolute maximum. Okay. And here, similarly, as x gets closer to 0 from the left, then y goes to negative infinity. So it also has no absolute minimum. Okay. So that's also possible. You can have a function that has both, has one, or has neither. All right. And then one more example. This is the one that might be a little more confusing, possibly. Let's take a look at this one. And let me do a better x-axis. Now, that's not much better, but you get the idea. Okay. What if you have a function like this? I just make a really simple one. It's basically just a straight line. Okay. Now, in this case, obviously, this is the lowest point. What this is here is the absolute minimum value. Remember, we're talking about the y value. The x location is basically where it is. The y value is actually the absolute minimum. What about this up here? Okay. Now, remember, the open circle means that point's not included. So, actually, here, there is actually no absolute maximum. And the reason why is what this means, the function is always going to get closer and closer to whatever this y value is. Let's say it's 3 or something like that, okay? It's always going to get closer and closer to that. We'll never actually reach it. So it never stops increasing, although it never gets higher than this point. It actually never stops increasing. It's always going toward that point a little bit at a time. So that means it never actually has a maximum value. Okay, although it's limited, it's different from the one we just showed here with the 1 over x. It's limited in that sense. Okay, this one is always goes towards infinity. It's always increasing or decreasing. This one isn't going to infinity, but still always increasing. It's always getting closer to this value. So that's an example of how you can have no absolute maximum, or if we also remove this point, this is an open circle, would be a no absolute minimum there as well. Okay. Now, a few notes I have on this. Let's come back on the left. These also these are called absolute extreme values or absolute extrema when you have absolute maximums or minimums. You may see that phrase or that word. These can be once can be at endpoints or between endpoints or at endpoints. It can be somewhere in the middle or at your endpoints. And once again, this is what I just mentioned here, the second bullet point. If a point appears to be an absolute maximum minimum like this, okay, if the point isn't included, then the function has no absolute maximum minimum there. That's what we just saw right here. Okay. And also remind you once again, the absolute maximum minimum value is the y value. Okay. The x is the location. So if we go back to this first graph I drew, right here, C is the location of our absolute maximum, but our absolute maximum value is actually the y value. You plug C in. In the same way here, D is a location of our absolute minimum, but the absolute minimum value is actually when you plug that in, you get that result. So that's the idea of an absolute maximum or minimum, an absolute case, the highest or lowest possible points. Now, the next one is related to that, something called the extreme value theorem. As if a function is continuous on a closed interval AB, and closed means it contains the endpoints, then it's guaranteed to have an absolute maximum value and an absolute minimum value on the interval. Okay, so let's look at an example of that. So what's going to tell me here, talking about the extreme value theorem. And so we can look at a graph similar to what we start out with. Let's say we have a graph like this. I think this is very much like the one we start out with. Well, let me change that a bit. Let's erase the whole thing. Do that one more time. Okay, here we go. All right, now the key parts here are that it's closed. Okay, so this is our A, and this is B. Okay, so it's not a closed interval, means it contains the endpoints. And it's continuous. And continuous means no breaks, no gaps, no holes in it. And basically, what that means is that As long as those three things are true, it has endpoints and as it's continuous in between, I'm guaranteed to have an absolute maximum or absolute minimum. Okay, that's always going to happen. Now, as we saw, if you had a gap or a hole in it, if it's like a piecewise function, or if your endpoints aren't included, possibly that might not be true. If you have asymptotes or something like that, so anything that makes it discontinuous, or if you're missing the endpoints, then that might not be true. But in a case like this always has an absolute maximum minimum. So continuous, just restate it on, it's called a closed interval. Basically guarantees an absolute maximum and minimum. Guarantees we have both. Okay. Once it's only if it's on a closed interval, it's continuous. If that's not true, that can throw you off. That's a useful function to have, because many of the functions you would use in real life will be like that. They will be continuous and they'll be on some closed interval. Okay. Now, so we talk about the absolute value, absolute maximums and minimum values. Now let's think about the what are called local maximum or minimum values. And the definition, the way it's stated, is very much the same. Okay, so it's kind of mathematical. But the only real difference here is we're talking about what's called an interior point, okay, not an endpoint. So we're not considering endpoints. So, but the same way, if looking at endpoints, looking at interior points, not endpoints, and some number C, X value of C, you plug that in, its Y is the highest Y around locally, close by, then that's what's called a local maximum. Okay, think of that as the top of a hill. Or if it's the lowest point around, doesn't have to be the lowest point everywhere, it's the lowest point around locally, that's why it's called local, then it's a local minimum. So let's draw a picture of this. Okay, I'm actually going to make several here. Okay, let's say this is our function. Okay, now let's label these. Let's say this point is A, B, C, and D. Okay, so if you notice here, think about it's kind of like much like a roller coaster or a hilly road. Okay, this top right here, this point right here, this Y value is the highest point around. Okay, so that makes it what's called a local maximum. Okay, so is this one. This is actually higher, but they're both local maximums. So we have local maximums at x equals A and x equals B. Now, the maximum values are the Y values, but you have local maximums at those 2 points. They're the highest points around. Also, as I mentioned here below in some of the further notes here, basically it's a local maximum is the top of the hill. It's also where the function goes from increasing to decreasing. Okay, it's true here and here, increasing to decreasing. Okay. Now, a local minimum then is the bottom of a valley. It's where the function, also where the function goes from decreasing to increasing. Okay, so we have local minimum values at x equals b and x equals d. Okay, and once again, those are the highest points or lowest points locally. They don't have to be the highest points at all. Now, one other thing I mentioned. So let's look over a couple of the notes we have. once again, endpoint of interval can be an absolute maximum minimum, but not a local maximum minimum. So actually, the endpoints don't count. So actually, if let's do another graph down here below. So a few more things could happen. Let's say we had a point like this. Now let's say this function actually comes to a point. Let's say this is our function. Okay. Now this, even though it just comes to a point, it's not what's called smooth. Okay. And actually, the derivative doesn't exist there. It's not differentiable there because your limits, think about your derivative is based on limits. The limits from left and right are not equal. But this is a local maximum value because it is highest, lowest. It also is actually the local maximum and an absolute maximum here. Okay. Local max and an absolute maximum in this case. All right. What about this point right here? Well, it's definitely an absolute minimum, but it's not a local minimum. Okay. And the reason why is because it's basically an endpoint. Okay. It's not what's called an interior point. This is the idea when I say here that a couple points here, a local maximum, it values the top of a hill. Okay. It's where the function changes from increasing and decreasing. To be a local maximum, both sides of the hill must be there. And also say here, basically the same thing, similar thing with the minimum. The local minimum is the bottom of a valley, like we saw in the previous examples. Okay, where the function goes from decreasing to increasing, and basically both sides of the valley have to be here. So here, there's only like one side of the valley if you think of it that way. So it's an endpoint or only one side of the valley. So this can't be a local minimum, which is strange, but just mostly just the way things are defined. Someone came up with this definition a long time ago, and that's kind of stuck, but that's essentially the way it's defined. So this is not a local minimum here. It is an absolute minimum. It's the lowest point in the graph, but it's not a local minimum. That's just based on the definition. Okay. And then one more thing to wrap up with this idea is if a function has a local maximum or minimum value, okay, like the ones we just talking about, and the derivative at that point exists, then it's going to be 0. Okay, because as I just said, hang on, let's see, I lost my train of thought in a second. So, yeah, so basically, if a local maximum, let's look back at this graph here. Okay, so local maximum like this one, okay, so where the function goes from increasing to decreasing. Okay, now for it to do that, then the function has to, if the derivative exists here at the maximum value, then it has to actually go through 0 to change there. So the function changes, if a derivative changes sign, okay, so here, remember this function is increasing, and derivative is positive. Over here, the function is decreasing, so our derivative is negative. And since the function exists, the derivative exists right there, it's what's called smooth, or it's differentiable, then it's got to be 0. So let's take a look at this idea here. Let's go down here. Let's draw another basic graph. In fact, I don't really need this so much. Let's just do it this way. So the graph like this. Okay. Now over here, f prime of x is greater than 0. Need some space. So over here, f prime of x is greater than 0. It's increasing. Okay. And obviously on this side, f prime of x is less than 0. It's decreasing. Okay. And since, right, this is kind of a smooth transition right here, at this point right here, the local maximum, think about our tangent lines, looks like this. F prime of x is equal to 0 at that point. Okay. And basically, both limits are going to that from the left and right. They agree that's 0. So, and the function exists at that point. So, The derivative is 0 right there. Okay. Similarly, we said right here through this point, our derivative is 0. Over here, our derivative is increasing. So our derivative is positive again. Okay. The function is increasing. And so if it's increasing, okay, then some point right here as well, then in between, the derivative has to also be 0 if that derivative exists and the function exists right there. Okay. Now, how could this break down? All right. Let's look at another graph, for example. Let's do a couple. So let's say we have something like this. Let's say we have a sharp corner right here. Let's say we have something like this. Okay, a function like this. Now, what's the problem here? Well, obviously here, once again, like the one we just saw, here our derivative is positive over here, greater than 0. It's negative here, just like it was above. Okay, but right here, f prime of x doesn't exist right here at the top because it's a sharp corner. Basically, it doesn't smoothly change from positive to negative, it just abruptly changes from positive to negative. So the derivative doesn't actually, the limit doesn't exist right there. Okay. And also, similar thing here, of course, over here, the derivative is positive, the function is increasing. But right here, the limit, the f prime of x doesn't exist right here because we have a hole in the graph. F prime of x doesn't exist. So the function, the statement says the function has a local maximum minimum value at c, and f prime of c exists, then f prime of c has to be 0. But these are some ways you can break down if you have a sharp corner there, or maybe you have a break in the graph where it's not continuous or something like that. Okay. Now, let's talk about a critical point. So we've kind of, some things we learned so far helped us develop this next idea of a critical point. So what we're going to do, if you notice, is that um, we talk about these idea of maximum minimums often involve like the top of a hill or bottom of a valley. And often, as you imagine in real life, you're often looking for things that give you maximums or minimums. Okay, you want to minimize cost, you want to maximize profit, you want to minimize your how much gas you use in your car. Okay, or you want to maximize fuel economy. The two ways of saying the same thing. Okay, these examples, a lot of times in life, you're looking for maximum or minimum values. You want to find out where those occur, and so those are going to occur typically at either absolute or local maximum values. And so what we're going to do is be able to find those. Okay, so what we've seen so far is if you have an interior point like this, okay, especially, and if you have an interior point of a function, okay, not the endpoints, and if it's a nice smooth function, okay, where basically it's continuous and it's smooth, in other words, no sharp corners, no holes, no gaps, then basically um, we want to, if we can find these points, these are local maximums or minimums, those will often be important points to know. And as we just mentioned, if we have those nice functions like that, those are going to be the places where the derivative is equal to 0. Or in some cases, it doesn't exist like it does here. Okay, so I actually want to look for both places where the derivative is 0 and also places where the derivative doesn't exist. That's what we want to find. And so those are what are called critical points. Okay, let's look up here. It says if an interior point, once again, not an endpoint, c of a function f is a point where the derivative is equal to 0 at that point, or the derivative doesn't exist at that point, then c is called a critical point of f. And the derivative function often changes at a critical point. That's why it's important. And often where the derivative changes sign, rather, where the derivative changes sign is often where you have a maximum or a minimum. Okay. Now, an endpoint is not a critical point. And this one, this just has to do with being a definition. Okay. Now, sometimes those endpoints will be the points where you have a maximum or minimum, but we can always just evaluate those from the function itself. So let's take a look at some things that are and are not critical points, or basically are critical points. So let's draw another graph. Okay, so let's say our function looks like this. Okay, let's say this is our function. Okay, so this is where our critical points are. Okay, a critical point is a place where the derivative is 0. So right here is a critical point. Okay, and here the critical points are the x values. So a, that's a critical point. Okay, also one here at b. Okay, so right here at a and b, your derivative f prime of x is equal to 0. And also right here at b, it's also equal to 0. Okay, top of a hill, bottom of a valley, right here. Now, what about here? This is also a critical point at c. And actually, this is the example we just said where it doesn't exist. Okay. Now, what about here? I'm going to call this D, where this asymptote is. And also, once again, here at D, f prime, both at C and D, f prime of x doesn't exist at both C and D. Okay. I'm trying to draw arrows there. Okay. So all these are four critical points. All right. First two are where your derivative is 0. Okay. We have a nice smooth top and bottom, nice smooth change from, in this case, where derivative changes sign from positive to negative. You're from negative to positive. Here, the derivative changes sign as well from positive to negative, but not smoothly, okay, abruptly. And here also, our derivative doesn't have to, can change sign at an asymptote like this. It doesn't actually have to, okay? It's possible you can be going to an asymptote from the same side, but still, this is a place where the derivative doesn't exist. The function also itself doesn't exist. And so this is a place where we have a critical point. And these are the points where the reason we're looking for this, and once again, these are places where you look for potentially for maximum or minimum values, or also places where your derivative changes sign. That can also be really important to know. Where you change from increasing, decreasing, or the other way around. Okay, so those are critical points. Okay, now how can we find a critical point? Let's practice with that just a minute. Okay, so number one, let's say we want to look at this function. Let me make sure I write this down, make sure I read it okay. So let's say we have this x cubed over 3 minus x squared over 2 minus 6x, that's equal to f of x. Okay, that's our function. All right. Now, with most functions, let's take a look at that on Desmos and kind of get a feel of what it looks like. So x cubed divided by 3 minus x squared divided by 2, and then minus 6x. Okay, looks like we need to zoom out a bit. Okay, so now we can see right away what this looks like. Okay, and also tell we have a couple places where this is, as we learned so far, this is a local maximum, the top of a hill. This is a local minimum, the bottom of a valley. So we have two of those. So I want to see if we can find those are actually our critical values, as we'll see in a moment. So let's see how we can find them. We're going to do it from the graph. Let's see how we can find it from just the function without the graph. So what we want to do then is we want to find the values, find the places where f prime of x is equal to 0 or doesn't exist. Okay, so you can imagine the first thing we need to do is find the derivative. So let's find f prime of x. Okay, so we take the derivative of this, so f prime. Okay, so this is the same as 1/3, so it's going to be 1/3 times the derivative of x cubed is 3x squared. Okay. Then minus, think of it as being 1/2 out front. The derivative of x squared is 2x. Then minus the derivative of 6x is just 6. Okay. Of course, here, this is got function is kind of made up this way. These 2's and 3's will cancel out. What we're left with then is x squared minus x minus 6. Okay, so this is our f prime. Now, if you want to know where that's equal to 0, now first off, remember that's a polynomial. It exists everywhere. All right, don't have to worry about existing, but where is it 0? Okay, so what we're going to do then is want to solve. Also, let me make a note. This exists everywhere. Don't have to worry about not existing. Let's define the other critical values. Let's solve f prime of x is equal to 0. So x squared minus x minus 6 is 0. Okay. Now, this is one, of course, you use a quadratic formula. This one will actually factor. That's the quickest way to do it if you recognize it. And this factors into x minus 3, x plus 2. Remember, set each one of these equal to 0 and solve. So x minus 3 is 0. X plus 2 is 0. And so we get x equals 3, x equals negative 2. So those are our critical values. Okay, as we look back at our graph again, that's what we saw. Okay, when x is negative 2, that's a critical value. That's a place where we have a local, in this case, have a local maximum. When x is 3, that's the place we have a local minimum. Okay, so those tell us the critical values of the locations of those. Now, whether they're now that doesn't tell us whether they're local minimums or local maximums. That just tells us their critical values where the derivative changes sign. Okay, where it's equal to 0. That's what it tells us. Okay, that's the idea. So what we're going to do then, we want to find the critical values of a function. And what we're going to do is take the derivative and then find where the derivative either is 0 or doesn't exist. So the next thing we want to do then is be able to find, take everything we learned today, put it all together, and find basically absolute extreme values, absolute maximum or minimum values of a function. So it says, let's assume a function f is continuous on a closed interval a to b. Once again, remember the closed, you have the brackets, that means it's closed, it contains the endpoints. And so remember, we close a continuous and closed interval a to b, then we're guaranteed from our extreme value theorem to have an absolute maximum and minimum value on that. So we're guaranteed to have those. The question is, where are they? So here's how we're going to do that then. So we have a function like this. What we're going to do first is find the critical points or critical values of the function like we just did here. So take the derivative set equal to 0. Evaluate the function at the critical points and at the endpoints. So the absolute maximum could be at one of these critical values, or it also could be at the endpoint. So we want to evaluate all of those. And then essentially, of course, then once we do that, the absolute minimum will be the largest y value we have. And then the absolute maximum will be the smallest y value we have. And so we also want to know what values give us, what values of x then give us those absolute maximum and minimum values. So let's come down here and let's do a few examples of this. So I want to find absolute maximum and minimum values. Okay, so let's take a look at a few. So number one, our function f of x is going to be x cubed minus 3x squared. And the interval we'll look at specifically, you know, this is a polynomial, it's defined everywhere. We want to look at on this interval from -1 to 3. Okay, here once again, our endpoints are included. Let's actually graph this as well. X cubed minus 3x squared. I'm going to turn this one off. And then this time graph y equals x cubed minus 3x squared. Okay. Now, once again, on the interval from -1 to 3. So -1 is right here and 3 is right here. Okay, so we get an idea what that looks like. Okay, so right here is -1, here's 3. So our function looks something like this. No, it doesn't include, I was going to erase that whole thing. Sorry. Let's try that again. Let me take a look at it one more time. Okay. So here is -1. Actually, here's 3. It looks something like that on that interval. Okay. Now, so once again, let's do the same thing. Let's call this part, or maybe call it part A. Okay. So want to find the critical points or critical values. Okay. So let's take the derivative. F prime of x is equal to, that's going to be 3x squared minus 3 times 2x. And so that's going to be 3x squared minus 6x. Then once again, next, set that equal to 0. So solve 3x squared minus 6x is equal to 0. This one can also factor. So take out a 3 and an x. You take that out. What's left? What's left from this first one? Just an x. What's left here is a 2. Once again, if you're unsure, just multiply it back through to make sure you get the same thing. As we did in the previous example, set each one of these factors equal to 0 and solve it. So we have 3x is 0, x minus 2 is 0. And of course, here, divide both sides by 3, x is 0. Here, add 2 to both sides, x is equal to 2. And that's what we saw in our picture, right? So those are our critical values or critical points. Okay. Now, what we're going to do then is we need to actually test all of those, evaluate. That's part B, so let's evaluate everything. All right, so we're going to evaluate are basically the 4 points, so the endpoints and also the critical values, okay? So basically we want to do it x equals -1. So the endpoint or interval went to -1 to 3. So x equals -1, x equals 0, x equals 2, x equals 3. So basically what we need to do is kind of like a little table, then f of -1, okay? Of course, you can plug that in the calculator or do it by hand. Let's see if we can get that from the graph. This point right here, yeah, -1 when x is -1, y is -4, okay? -4. F of 0, I believe that was just 0. Yeah, 0, 0. And then here 2, -4, then 3, 0. F of 2 is also -4, and f of 3 is also 0. So let's take a look. Then kind of our part, we can actually put part B. This is part B. Let's do part C right beside it. I'll draw a line to separate that part C. Okay. So then our absolute maximum values, okay, actually we have 2. All right. The highest value we had are actually at 0. All right. And that was at x equals 0, x equals 3. They both had a y value. The absolute value itself was 0. The locations are x 0 and 3. Okay. Then we had the absolute minimum values at the other 2. So at x equals -1, x equals 2. Those locations are absolute minimum. Okay, so that's the idea. So basically just find your critical values, evaluate them in the function, also evaluate your endpoints of the function, then compare everything, find what the maximum minimum is. Now, in some cases, we may not have, like this, we're guaranteed to have maximum, but in this case, we had more than one value give us a absolute maximum or an absolute minimum, and that's okay. That can happen sometimes. Okay, next one, number 2. Oops, that was a stray mark. Get rid of that. Okay, so number 2, let's go to our next page. And this time, let's do this function. So um, but this time we have our f of x is equal to cosine squared x, and then on the interval from 0 to pi. Okay. Now also remember, this is the same thing. Anytime you see this, this is the same thing as cosine x squared. Okay. It doesn't mean take the cosine of x twice. Take the cosine of x and take the cosine of that. It means cosine of x squared. Just remember that. Let's also look at it. Let's graph this. So actually, I'm going to graph it as that is cosine x squared. So y equals cosine of x. And also we're default in radian mode, then squared. Notice it's similar, except of course being squared, everything has to be positive or 0. Okay. Now interval from 0 to 2 pi. Okay. Sorry, 0 to 2 pi. So here is 0 and here's pi. Okay. So basically that's just kind of one period of this function. So a small graph of that looks like this. Okay. Now, as we can see, looks like it appears we have, look like these locations are probably both absolute maximums, and it looks like absolute minimum right down here. That's what we'll have to find out. Okay. So once again, let's take our steps. So part A, find our critical values. Okay. So f prime of x is find the derivative. I'm going to use this version right here. So remember, the derivative of something squared. This is the chain rule. Something squared is 2 times of something. So 2 times the cosine of x. Then the derivative of cosine of x is negative sine of x from the chain rule. So just make it look a little bit better. So we here have negative 2 times the cosine of x times the sine of x. Okay. Now we want to find where that's equal to 0. So I want to solve f prime of x is equal to 0. Okay. So this, hope you remember doing solving some trigonometric equations in trig class. That's what we're doing. So we have negative 2 cosine of x times the sine of x, okay, is equal to 0. Now, the first thing I'm going to do is I'm going to divide through by negative 2. We can do that. It's a constant. That'll just make everything simpler, okay? That's going to give us cosine of x times the sine of x is equal to 0, okay? Divide through by both by negative 2. Now, in the same way, if either cosine of x or sine of x is 0, makes the whole thing 0. So I can essentially solve each one of these separately. So the cosine of x equals 0, and then the sine of x equals 0. Now remember here, we're also on this interval on 0 to 2 pi. 0 to pi, not 0 to 2 pi, 0 to pi. Okay. Now, sine of x, so where in this interval is, and actually technically here, we're just looking at the interior, so we don't really count the endpoints, okay, for our critical values. So this is just, sorry, I'm having a hard time writing simple stuff with the pad tonight. Okay, don't count the endpoints, all right? So remember, what values is cosine x going to be at? If x is, for example, pi over 2, or multiples of pi over 2, okay? And sine, in fact, it might be good to just go back and graph those as well. So let's actually let's turn this off. Let's graph both sine, just regular sine and regular cosine. Okay. So from 0 to 2 pi, or 0 to pi, okay, the only place where cosine is 0 is right here at 2 pi over 2, as we just said. Okay. And what about sine? Let's get rid of this. So actually, on that interval from 0 to pi, sine isn't actually negative anywhere. Okay. So sine of x is here. There is no solution to this part of it in or on 0 to pi. 0 to pi. Okay. course, it's zero at both. It's sine is zero at both x equals 0 and x equals pi. But we're not including the endpoints. Okay. So, but this is our critical value, the critical point. Just 1 in this case. Okay. Now, so part B, we wanted to evaluate those. Okay, evaluate all three, so have our endpoints. So x equals 0. Then we have our critical value, x equals pi over 2. And then finally, at x equals pi. Okay, so f of 0, let's take a look what that was. All right, remember our function is cosine squared, or cosine of x squared. The cosine of 0 is 1. That's 1 squared, or 1. Okay. Cosine squared, a cosine of pi over 2 is 0. So f of pi over 2 is 0. Squared to 0 squared is 0. And then f of pi, when x is pi, cosine is 1. They're actually negative 1. But if you square negative 1, you get positive 1. Okay. And then finally, part C is basically find your absolute maximum minimum value. So actually, once again, we have two absolute maximum values at x equals 0, x equals pi, and we just have one absolute minimum, and that is at x equals pi over 2. And that's what we saw in our graph. Let's look back at our graph really quickly and take a look. Turn these off. Okay, right. So here's our original graph, 0 to pi. Right, here's 0, here's pi. Right, so these are both the same height. These are absolute maximum values of 1 at 0 and pi, and absolute minimum value of 0 occurs at pi over 2 there. Okay, let's do one more. Now, this one, a little bit more involved, but as we'll see, it's not that bad. We have to practice with another rule. This time our function is x over, or divided by x squared plus 3 squared. And this is on the interval from -2 to +2. Okay, so first off, let's graph that so it looks like we did the others. Let's just turn these off in case we need them later. So y equals x divided by, then parentheses, x squared plus 3 raised to the second. Okay, now if you notice, this one, there's no asymptote at 0. Okay, notice there's no asymptote anywhere. And there's also, it's defined also everywhere. The reason because of that is because our denominator is always going to be positive. Actually, always going to be positive, except by always going to be positive or 0 will always be positive. The denominator will be, because x squared, of course, is always going to be positive or 0. It's plus 3. Right. Now, this one actually has, we have to kind of zoom in a bit, actually has a bit of a wave to it. So what I'm going to do is actually I'm going to change our setting. This is probably be our last one we'll do for today. So let's actually change our vertical height settings. So make it a little bit easier to see. So go to the little wrench there and change the y values from negative 0.1 to positive 0.1. And that should give us a better view of this graph. Yeah, there we go. Okay. I can zoom out just a bit. That gives us a better view. So we change the settings. Okay. So clearly we can see what this graph is doing between -2 and 2. All right. Looks like we should have an absolute maximum or minimum value right here. Looks like we have should have an absolute maximum value right here. Okay. That was at 1. So I get -1. Okay. So let's make sure that's what we get. All right. So once again, the same process as before. Okay. So part A, find the critical value or values. It appears we're going to have 2s. That's the whole thing to do with the graph as well. Make sure that's what we get. All right. So f prime, so what you do is you actually use the quotient rule. Okay. Now the quotient rule, remember what it said. You can also use the product rule, making this writing the denominator is and the numerator with a negative exponent. I'm just use the quotient rule for practice. So what the quotient rule says, remember it's a fraction. Let's actually do the denominator first. And basically, it's the denominator squared. So that's going to be x squared plus 3 quantity squared, but this whole thing itself is squared. Okay. And then up here at the top, what we have is it's the bottom function first. So x squared plus 3 squared times the derivative of the top function, which is derivative of x is just 1. Then minus, and this is why the quotient rule, the order is important. We have a minus here, times the top function, which is just x, times the derivative of the denominator, which is going to be, using the chain rule, 2 times x squared plus 3 to the first, and then you have the chain rule, the derivative of the inside, the derivative of x squared plus 3 is going to be 2x. Okay? Now, let's keep going. Let's write that a little bit nicer. So our denominator, remember our exponents, if something squared, then square that again, it's going to be to the 4th power. So x squared plus 3 to the 4th. Okay. Now here we just have first x squared plus 3 squared. And here we're going to have minus x 2x times 2x going to be 4x squared times x squared plus 3. Okay. Now, let's probably have to do a little bit of algebra. So our denominator is the same for now, x squared plus 3 to the 4th. I'm going to factor an x squared plus 3 out of both of these. So it's going to be x squared plus 3. And that's going to leave me with, I still have an x squared plus 3 left in the front. Then minus 4x squared. I hope I'll explain why I'm doing all this. So this part is a bit of a pain. It's a little bit of algebra. So x squared plus 3 to the 4th. Okay. Now let's combine our like terms here. We're going to have is x squared plus 3 times, if I combine our like terms, is going to be, looks like it's 3 minus 3x squared. Okay. Now, remember, next thing we want to solve f prime of x is equal to 0. And I actually need to check something. I need more space. Hang on. So I can move this up. There we go. Then delete this. Okay. I may need more room, so let's do at least another page. It should be more than I need, but just in case. Okay, let's go back where we were. This one is a bit of a pain just because of all the algebra we have to do. Okay, so I want to solve that. Now, if you remember here, we said our denominator can't be 0. Okay, the only thing that could be 0, because actually if the denominator is 0, it makes the whole thing undefined anyway. It can't be 0, but if it could be 0, just make it undefined, not 0. So to solve this then, set equal to 0 and solve, just solve the numerator equal to 0. That's going to be x squared. So once again, so denominator can't be 0. Okay. So just have to set the numerator equal to 0 and solve. Okay, so that's x squared plus 3 times 3 minus 3x squared, okay, equals 0. Now, like we did before, this is in a factored form, so I can set each factor equal to 0, because if either one is 0, it makes the whole thing 0. So x squared plus 3 is 0. and make sure plenty of space, 3 minus 3x squared is 0. Okay, now, I think it's going to help us at least make this quicker to work with, happens right here, is, of course, if you get the x squared by itself, subtract 3 from both sides, you have x squared minus 3. So this basically has no real solutions. We can solve it, but it'd be imaginary. So that's not going to affect our problem. So here we have no critical values from this part. Okay. This part here is not going to give us any critical values because we don't get any real solutions. It'd be imaginary. Now over here, that's not the problem, as we'll see. Subtract 3 from both sides. We have negative 3x squared is equal to negative 3. Divide both sides by negative 3. Get x squared is equal to 1. This will give us real solutions. So remember, the way we do this is x is equal to plus or minus the square root of 1. And that's just x equals plus or minus 1. And so those are our critical values. Okay, those are our critical values. We have 2. All right. So for part B, okay, is where our evaluation step. Evaluate our endpoints and our critical values. So we evaluate x equals negative 2, x equals negative 1, and then at x equals 1, x equals 2. We have 4 to evaluate, so we want to plug this in, plug all these into our function. So f of negative 2, let's see if we can get that from our graph. Maybe not. Okay, actually, I believe we can. Well, almost. I get approximately, it's about negative 0.04. So we may just do this the long way. So we're almost there, but bear with me just a bit longer. We're almost there. All right. So basically, that's going to be our functions start off with x over x squared plus 3 squared. Okay. And that's equal to negative 2 over x squared. Well, x is negative 2. Okay, that's going to be negative 2 over 4 plus, this is going to be a 4 plus 3 is 7 plus 2 is 49. Okay, and that doesn't reduce. All right. Now let's plug in negative 1. We'll just do this by hand, I guess. F of negative 1 be negative 1 over negative 1 squared plus 3 squared. Okay. And so that's going to be negative 1 over negative 1 squared is going to be 1 plus 1 is 4. 4 squared is going to be 16. And then should have basically have some symmetry here. So a symmetric graph. So f of 1, I guess, should be probably positive 1 over 16. So 1 over, I realize I'm kind of running out of space down here, but you get the idea. And yeah, that's going to be positive 1 over 16. And then finally, this one, yeah, the only thing that's changing is just going to be it's positive or negative on top. And so this one is going to be f of 2. I'll just go and tell you it's just going to be positive 2 over 49. Okay. And so we compare those then, as we saw in the graph, these two, we have our maximum value here at 1, the minimum value at negative 1. And so part C, we have an absolute maximum at x equals 1 and an absolute minimum at x equals negative 1. Okay, and once again, that's what we saw with the graph. Okay, right there, minimum at negative 1 is our absolute minimum on this interval right here. Is our absolute maximum on that interval. Okay, so what did we learn today? So we learned about absolute maximum, minimum values, what those are. We learned about local maximum, minimum values. Also learned about critical values. So, and all these things will be important because obviously when you talk about maximizing something, find the maximum, minimum value of something is really important in real life, trying to real life functions in many applications. That's what we're looking for, is ways to help us find the maximum or minimum values of a function. Thank you. Have a good day.